So mostly today you're going to be hearing from Tim. I'm just going to be setting the stage a little bit at the beginning, um, and particularly trying to think about the way that my research lab at MIT is. Yeah, cool, you're fine. We're like double checking that all of our sort of transitions are all going to be good. But yeah, the way that my research lab at MIT thinks about the kind of fundamental bottlenecks between these two disciplines. There's an incredibly rich history of really amazing development in both areas, and we think the biggest pinch point is just that transition. How do we go from increasingly machine learning labeled data into the actual types of ecological inference that we're interested in without introducing a bunch of additional complexity, bias, and potentially risk. So the first thing that we wanted to do, so we are going to be working through the code, particularly in Google Colab. So hopefully this is something some of you are familiar with. If not, you can follow this QR code. And the reason we're getting you started right away is there is a preliminary data set download. So you'll go ahead and open this link. And then the most important thing is it's view only, but you'll need to actually make a copy of this in your own Google Drive so that you can actually work in it. Otherwise, it's going to complain and say you don't have access. Um, and then you're going to run the first cell. So this is going to be quite similar to running cells in like R or Jupyter Notebooks if you're familiar with them. But running that first cell will actually just start the dataset downloads. You can hover over the first code cell and click run. And so this, as you kind of get started in the background, it'll let the data download so that while we're talking to you about what we're actually going to be doing in the code part, you're kind of ready to go right when we get transferred over to code. Cool. So, and maybe also someone could put the link in the chat, Jody, if that's possible. Thank you. Cool. So setting the stage, why AI? Well, hopefully all of you have seen kind of some dimension of AI being used in ecology at this point, particularly if you're quantitative ecologists. I think that AI poses a pretty significant promise in this space, and I've been working on building AI models for specifically processing camera trap and bioacoustic and satellite and iNaturalist data for about 12 to 13 years. And we're starting to see these models get really good. So for a long time, it was just, me and others building machine learning models that kind of worked sometimes and could potentially be demonstrated in a paper to be successful or accurate. But then often when we moved to the real world, we would see some pretty significant degradation of that performance. And as a result, it meant that these models were not as useful. And we found ways to work around that. We thought about mechanisms and systems to actually focus on that generalizability, try to build tools that would help us process this incredible volume of ecological data that is being collected every day, and the amounts are increasing because the sensors to actually enable us to collect this data are becoming a lot cheaper. And there's been a lot more focus on data recently. And so as the amounts of data are growing sort of far outstripping our expert capacity to process that data, extract the actual sort of species observations that we might be interested in modeling downstream, we've really had to push for generalizable tools to automate that process. And so the first kind of generalizable tool for camera trap data is one that I published, back in 2018 when I was a very young grad student. It's called the Mega Detector. And that model was actually explicitly designed to generalize well, which meant that it could be used off the shelf for a lot of people. But part of what made it generalizable was that we didn't try to solve the hard problem of species identification. Instead, we recognized that we needed to move to animal detection, just finding and localizing animals in these images. That's still saving humans a lot of time. You still need to do some quality control and review, but it's not actually moving all the way to species. Now, these days, and actually explicitly today, and I'm pretty excited that we're going to be able to be some of the first to kind of demonstrate the capability, the Wildlife Insights and Google SpeciesNet model that I've been working on for probably 7 or 8 years now, has just been released. And so this is the first, I would say, true foundation model for species ID in camera traps. And we're going to be using that model today. And you can see that as the capabilities of these models increase, their kind of readiness for direct end-to-end deployment in something like occupancy modeling is much, much more ready. So very, very excited to walk through this with you today. And another important point, and the other kind of big point that I want to make before I hand it off to Tim for him to demonstrate his really, really cool work to you, is why Python? So we're doing all of this in Python, right? We're sort of talking through this entire thing end to end and using Python to both do what has always happened in Python, which is the machine learning research. 99% of machine learning research happens in Python. And that's really not changing. But we're also going to do the occupancy modeling in Python. And this is something that has historically not been true. So I would say that one of the biggest bottlenecks that I've currently found at that intersection, at that translation point between processing camera trap or other biodiversity data with machine learning, and then modeling that data, has been this significant translation barrier between two communities that have two preferences in coding languages. So the vast majority of ecological researchers that I work with work in R. And by far the vast majority of AI researchers work in Python. And it turns out that there are not so many people that are fluent in both. And as a result, we end up having machine learning researchers kind of refuse to work in R and do the statistical modeling, and ecological researchers who refuse to learn Python and want wrappers around the Python machine learning things in R so they can work in a language that's familiar to them. And what I've found is that type of wrapperization, this kind of translation point happening just like through some sort of weird code translators, it's brittle, it tends to break, and as a result, it tends not to actually be maintained and supported sufficiently. So I'm not saying that you guys should not use R anymore. That would be a pretty sensational take. But I am saying that for this group of community, this community that's trying to bridge this gap, that type of end-to-end research, being able to do it all in one language, I think is going to be huge. And recent libraries that have come out that enable more of the probabilistic modeling to happen in Python have really unlocked this as a capability. So we're trying to build a little bridge and do everything end to end in one language. I think actually for the first time, really, like at scale. And hopefully you guys will follow along with us on this journey. And if someone wants to re-implement all of machine learning training in R, they're also more than welcome to try. Cool. Okay. Pass it off to Tim, who's going to talk you through occupancy modeling end to end in Python.
Thank you so much. Awesome. Yeah, so what we've been working on over the past couple of months is this library we call BioLith, which stands for Bayesian Ecological Modeling in Python. And as the name suggests, it's written in Python. So again, our hope is that this might convince more machine learning oriented researchers to work more on ecological modeling and basically remove this initial language barrier to entry to ecological modeling. BioLith is written in NumPyro or using NumPyro, which under the hood uses JAX. And this is just to prevent any kind of confusion. This is JAX, not JAGS. And so JAX is great for one very specific reason, namely that it allows to run these models using GPUs. And so depending, on the size of your data and the type of your model, this GPU acceleration can make the whole model fitting process much faster. So far, we have 4 different occupancy models that are implemented in BioLith. Down the line, we plan to implement a lot more occupancy models, but also just other types of models. So, for example, one model that is planned is camera trap distance sampling. So right now, there are only these 4 models, and overall the library is very bare bones. But it's also super customizable, and it's very easy to implement your own models if you so choose. And just to kind of try to drive this point home, I like to show you this piece of code, which is a very simple occupancy model implemented using NumPyro and Biolith. And yeah, as you can see, I'm not going to walk through this code in detail, but this is basically all it takes to implement this type of model. So even if your model of interest is not implemented currently, it's very easy to add. So I assume that most of you are probably familiar with occupancy modeling, but just for those who aren't, I would like to give a super brief intro of what we're trying to do using occupancy modeling. So imagine you have a bunch of observations of different sites. So the sites in this case are 1, 2, 3, 4. And then you have observations over 3 different time opportunities. So T1, T2, and T3. And each observation can either be 1 for you saw your species of interest, or 0 for you didn't see the species of interest, or not a number, and then if you don't have any observation at that time. Right? Now you're trying to answer which site is how likely to be occupied given these observations. So what you're basically trying to do is account for false absences in your observation data, right? Because at any given point in time, you might not see the species of interest, even although it's there. And so then usually you're also interested in the probability of detecting your species of interest if it's present. And then ideally, what might be ecologically most interesting is which environmental factors do actually influence occupancy probability, right? So we also call those covariates. So just to set the stage of what we're trying to do in this session, we'll be fitting single season occupancy models. We'll be focusing on a single species. I'll walk through some examples using wolves. And we'll treat our image classifier as a binary classifier, which is either going to predict that a species is there or it's not there in a given image.
Oh, and just a point there. So the model we're using is trained to predict a lot of different categories.
Yeah.
So it's trained to predict actually thousands of different species, but you can use any what's called multi-class classifier, like this one that predicts thousands of different species, as a binary classifier by just taking it and treating it as one versus all. So anytime it predicts wolf with high confidence, we treat that as a wolf. And if it predicts anything else, we treat it as not a wolf.
Exactly. And to do that, we'll be using logits instead of probabilities that the classifier outputs. And this is just easier to work with, especially in this case, where we basically treat our multi-species classifier as a binary classifier, just because the logit predictions for each species are independent of what is predicted of the other species, right? Which wouldn't be the case if you would apply softmax, for example.
So you might not be familiar with the concept of a logit. I'm not sure. If you aren't, essentially what most machine learning models are going to output some vector at the end, which is going to be not calibrated numbers, like they're just sort of real numbers on the real line. And then what we often do to translate that vector of output predictions, which is in a logit, to something that looks maybe more like a probability in that it sums to 1 over the entire vector, is we take a softmax. And so because once you take a softmax, you're sort of explicitly enforcing that everything sums to 1. That's where you get that dependence across the categories. But if you actually just work directly with the logits, you're not forcing that same kind of like remapping. And so you keep kind of more of the information and you can treat the categories more independently.
Yeah, exactly.
Yeah.
Thank you. So yeah, overall, we'll be basically trying to do the simplest thing possible to use a machine learning classifier to do occupancy modeling. So this is not going to be the most advanced type of model that you may know, but it's the simplest to demonstrate the whole workflow.
And show that it's possible to do it all end to end.
Exactly.
Which is what I'm very excited about.
Yeah. So if you think about traditional occupancy modeling, you have your observations at time t. And again, we're going to use images for this, but it's very similar if you, for example, do passive acoustic monitoring. So you got your observations at time t, and you usually have some kind of human expert screening those images. And so then you're looking at a bunch of images in a specific time interval. And you're not going to see your species of interest probably for a while. And then at some point you might. So your observation is now 1. And then you can use this observation to fit your occupancy model, right? So this is how it's traditionally done. And you can use super simple and established occupancy models for that. So for example, the original McKenzie occupancy model, where you basically model your observation as coming from a Bernoulli distribution. And then, so given your site is occupied and it's 0 otherwise. And then you can have a bunch of covariates influencing your occupancy probability and also your probability of detection. Now, if you introduce machine learning classifiers into this mix, you again have your observations, but now your classifier is going to output a bunch of scores, logits in this case, right? And so as you feed in images, you can build this kind of histogram of different logit values. And so how do you then go from this collection of logits and fit your occupancy model, right? This is what we're trying to do. And the first difficulty is no matter how you choose your threshold, no classifier is perfect, right? And so you're always going to have some false positives. So observations that don't actually show your species of interest, but according to your classifier, they do, right? And so the first thing we have to do is account for false positives. And usually this is done by introducing an additional false positive probability given your site is unoccupied, right? So this is the bold part right there. And the rest is basically unchanged.
And an important note here is that the machine learning models are going to make mistakes in both directions, right? Like no model, you can't guarantee any model is perfect. And so you'll have false positives and you'll also probably have false negatives. But the false negatives, you can assume, can be rolled into the probability of detection for the entire system, right? Because you already had the probability that you were going to miss something due to the actual sensor.
Right.
But now those false positives, that's something that previously you had the assumption didn't exist because you assumed that the human doing the labeling was perfect, though in my experience, that's not always true.
Yeah.
But so the false positives are the thing you actually have to adapt the ecological model to be able to handle.
Yeah. And yeah, this has been done in 2006. So this is also nothing revolutionary by this point. But it's just something to note. Then probably the most important step is finding a good threshold. And again, I'm gonna do the most naive and simple thing here, which has turned out to work well in practice. And so in general, if you choose this kind of threshold, you want to make sure that you don't have too many false positives, right? But you also want to have enough observations to actually successfully fit your occupancy model, right? So it's kind of a trade-off. And so what you can do is look at the histogram of logit values that you got from your classifier, and then just sample uniformly across the whole range and just look at images corresponding to those logits, right? And so say we're interested in wolves. So this is very clearly not a wolf, as our classifier clearly notices. So we're going to label this not wolf. We're going to sample this image with a high logit, and this is clearly a wolf, right? So we're going to label this a true observation. And then we will probably have a lot of samples in the middle, where the classifier is not super sure whether there's a wolf there or not, maybe just because the image quality is bad or the animal is not clearly visible. And so we can do this for a bunch of images, and then build this type of histogram where we have a sample of false observations, so images that don't show our species of interest, and then a set of true observations containing our species of interest. And then from that, we can build a precision and recall curve. We do this by basically sweeping over all possible logits and then just plotting the precision and recall pair for each of them. And what we're going to get is this type of curve, where basically you can have either, sorry, I'll do this again.
Such a cool visualization, Tim.
That's the only reason I did that. So yeah, just see this again. So yeah, you can either have super high precision, because you're basically having a super high threshold and rejecting most images, right? So you're going to be super precise, but have low recall because you're not actually capturing a lot of the true images.
And just to clarify, precision and recall are very, very common metrics in machine learning, but if you guys aren't familiar with them, precision is essentially measuring of how many things you say are in fact your category of interest are actually your category of interest. So very high precision would be everything you say is a wolf is actually a wolf, but it doesn't tell you anything about the wolves the wolves you didn't say were a wolf. Whereas recall is like almost a bit of like the flip of that. Not quite, but it's looking at the other side of the equation, which is of all the real wolves that were there, how many of them did you find? And so there's this trade-off between precision and recall. And often when we're talking about measuring performance of a machine learning model, we'll look at something like one of these precision recall curves where we look at different possible thresholds and we try to sort of pick the best model based on the actual needs of the user in terms of that trade-off between how precise versus how much high recall you need. Yeah.
And so what we found in our experiments so far is that basically taking the threshold that maximizes the F1 score is a good strategy. And the F1 score is the harmonic mean of precision and recall. So it's graphically, at least, it's going to be somewhere here. And so in this case, the optimal threshold with the optimal F1 score would be around 5, which seems about right. And I would like to note that this is very empirical. It's probably not optimal to do it this way. it's probably not optimal in the number of images you show to humans to label. You could probably, get away with less images. But it's a very simple strategy that seems to work well across a range of data sets and across a range of species that have varying detection probabilities. Just because probably the F1 score kind of naturally balances kind of how many false positives you kind of it minimizes the number of false positives, and it maximizes kind of the true images, the true samples you actually use for fitting your occupancy model.
And an important note here also is that, like I was sort of mentioning at the beginning, if your machine learning model is not very good, this gets a lot harder, right? Because that precision recall curve is going to be like super low across the board. There's probably going to be a lot of true positives you miss, and you're going to be predicting a lot of the wrong things. And so as the machine learning models get better, this threshold selection also gets a lot easier. There's more separability in that logit score between the two categories that you're looking at. So as machine learning models have gotten better and better over time, it's made this type of thing more and more possible to do in a way that feels more statistically sound.
Yeah. And this is also super apparent in this precision recall curve, which is normally you will get something like this. I don't know if you see my cursor, but yeah, I guess
closer to the diagonal.
Closer to the diagonal, exactly. Cool. Okay, so this is the strategy we're going to implement in the code. So for anybody who hasn't yet opened the Google Colab notebook, I encourage you to do so now. You can just follow this link or scan the QR code. And I'm gonna keep this open maybe for like 10 seconds.
I was also gonna say, I think there were a couple questions, and so maybe we could address them before we move to the demo.
Yeah, sounds good.
There we go. Were there any questions? Feel free to speak up. If not, I saw some hands, but I wasn't sure.
Nope, I don't think so.
Never mind.
The questions we've got in Poll Everywhere seem like ones that'll be good to check in with you about at the end. So, yep, I think we're good to keep going.
Awesome. Okay.
We are going to move. Oh, there we go.
Oh, Jesus. Okay. So this is one of the issues.
I don't know.
I don't know.
Here.
I think it's shared.
Can you guys see the code, or do you see the slides?
We see the code, but it says runtime disconnected.
Okay. Yep. Anyway, so this is one of the annoying things about Colab. So now.
Yeah. So I'm gonna switch over to our local notebook instance
because we anticipated this might happen.
Exactly. So it's gonna look slightly different than for you, but it's gonna run the same code. So yeah, feel free to just follow along here. I also note if the download is still running for you, that's absolutely not an issue. The code will work without all the images downloaded. So feel free to just stop the cell if it's still running. And yeah, I'm gonna switch over.
Yeah. Okay, cool. So this is the exact same code, just running locally, just because we wanted a fail-safe in case Google Colab disconnected.
Yeah.
Google Colab is an amazing tool. It's basically like Google is for free running a lot of the computational stuff on one of their data centers, and you're just able to access it directly from the browser. This is great for this type of thing because you don't actually need to install Python on your computer and install the packages and the dependencies. So it's great to just like try things out. But the frustrating part is sometimes the runtimes get disconnected. Like if your Wi-Fi cuts out for a second, you might have to restart, which can be annoying.
Yeah. I'd also like to add that Google Colab is great for sharing code. with your colleagues. So you can just go up here, click share, and just copy the link, send it to somebody for work on stuff. So yeah, it's also great for that. Cool. So first, I'd like to talk a bit about the data set we're going to work with, that some of you hopefully had the chance to download. This is an open data set licensed under the Open Government License. And it's a camera trapping data set that was collected between 2020 and 2021 around the Chernobyl exclusion area. So that's already a super cool location to do camera trapping, I think. This is the area the data set was collected in. I think Chernobyl is around here somewhere. So just north of Kiev. And yeah, let's just look at some example images to get a feeling for the data set. So yeah, this is a wolf. It's the main species we're going to work with. And there are also some links in there, which is super cool. I guess another cool fact about this data set is there was a forest fire in 2020, just before they set the camera traps up. And so there might be some interesting, shifts in occupancy or, animal distribution in here. Okay, so that's all I wanted to say for now about the data set. So now we're going to set up our classifier. And as Sarah briefly mentioned, we're going to use the classifier that is used for wildlife insights. The classifier itself is called SpeciesNet, and it's available at this link. This up real quick. So yeah, this is the GitHub for this classifier. Again, it's open source since a couple of minutes ago, which is awesome. And so yeah, we're going to use this. Unfortunately, the main code base doesn't support extracting logits yet, and it only outputs probabilities for the top 5 individuals currently. So this is one instance where you might want to actually customize an existing code base, an existing machine learning code base, to slightly modify it and do what you want to do. In this case, I already did that for you, so you can just run this cell to basically install this plus my modifications.
And all that modification is doing is it's giving you those raw logits over the entire categories, which is very easy to do because the entire model and the weights and the code is open source. So you're just basically, instead of outputting a processed output, you're outputting an unprocessed output from the model.
Yeah. Okay, so now we're gonna define the set of species of interest. In theory, you could just extract classification scores for all species that are supported by this classifier, but then your prediction, output file would just become very big. So in this case, we're just gonna extract those species we are actually expecting to be present in the data set. If you want to take a look at the full list that is supported, you can just follow this link right here. And we can take a look real quick. This all right here. So yeah, as you can see, so each line corresponds to one species. There's some taxonomy. The species name is basically the rightmost column in each row.
Or the common name. And then,
Yeah,
and
right.
then
The
the
common
species
name.
name is the two before it, genus and
Right.
species.
Yeah.
Tim, could I have you zoom in a little bit? It's hard to see that. Yes, that's so much better. Thank you.
Awesome.
There's close to 3,500 species in this model. It's only the species that there was sufficient training data to expect that the performance was reasonably good. And of course, the performance is not exactly the same for all of these species, but it's very exciting that we now have a model that is reasonably good at 3,500 species for camera traps. I think that's a big jump forward, and particularly in terms of open source models that are then very flexibly usable and modifiable.
Yeah. And I guess even though this is only around 3,500 species, chances are, your species of interest is probably in here. And even if your exact species isn't in here, you might still be able to use this classifier if there's a similar species.
Yeah. So do some like hacky remapping of like things that might look similar but exist in other places.
Yeah.
Or work at a higher level of the taxonomy. So predict at the genus level, for example.
Yeah. I'm gonna zoom out slightly. Okay, I think this is good. So yeah, these are our species of interest. So we got the European hare, the moose, gray wolf, which is the main one we're working with, and a bunch of others. And we're just gonna save those into a text file so we can use it in the next step. Okay, so now we're gonna run the classifier on the entire set of images that we downloaded. And this is super easy to do. You basically just do this. And obviously, I've already done this, so I'm not going to run this again. If you haven't gotten to this point yet, I suggest you don't run the cell because it's going to take around 20 minutes for all 10,000 camera trap images in the data set. And instead, you can just run the cell below to just download the predictions we've already created. Okay, so let's maybe take a look at the format of the predictions. So for anybody who doesn't recognize this format, this is a JSON file. So it's basically a bunch of nested dictionaries and lists that contain the predictions. So we're going to want to look at this kind of dictionary key, which contains an array. And then there's one such huge dictionary for each file. The file is, given here in the file path. And then we have a bunch of classifications. We are mostly interested in those. Sorry. So again, this just repeats our target classes, the classes we've decided we want to focus on. And then this is just the list of logits that the classifier outputs. So yeah, in this case, this is pretty high. So I'm guessing this is probably an image of a moose. We can take a look. Yeah, maybe. Hard to say. There's definitely something there. I'm not sure it's a moose.
Anyone who works with camera trap data knows that characteristic eyeball blur.
Yeah, exactly. Cool. So now we're going to work with this data. And to do that, we're going to import a bunch of Python libraries. JSON is just the one we're going to use to read the file we just looked at. NumPy is a library to do efficient vector and matrix math. Pandas is for working with data frames. And then matplotlib and pyplot is for plotting. So we're going to run this. Okay, cool. So we've got our predictions. Now let's load in the metadata of the camera trap data set. There are two different metadata tables. And so we're just going to load both of them and then merge them into a single table and print out the first couple of rows. Cool. So yeah, this table is basically a row for each camera trap. And we're primarily going to use this to get some covariates for our occupancy model. And there are a bunch of different interesting covariates we can use. So for example, there's the geographical location in there, right here, these two columns. We've got a measurement of radiation dose in microsieverts, which is super cool. So yeah, this is about 1 microsievert per hour. So not great, not terrible. And yeah, then we also get an assessment of the degree of burn of the area the camera trap was set up in, which we can also use as a covariate. Sorry. Cool. So to be able to use the degree of burn as a covariate, we're going to convert that into a numeric attribute, basically going from 0 to 4, I think. And we're also just doing some magic to use the camera location as the key in this table, or the index.
I think you ran it twice.
Oh, yeah, it's probably true. Okay. Cool, so we got the location metadata. Now let's load in the image metadata. Cool, so basically what we're doing is we're reading the downloaded CSV, which contains a ground truth label for each image. We are not going to use the ground truth labels for most of this, because we want to use the classifier scores. But just in case you want to use those, the ground truth labels on here.
And it's nice because we can use it to evaluate.
Exactly. We're going to pass the datetime, which is going to be important for later. Basically just going from a text format into a format that is, that we can do arithmetic with. We're also gonna define a mapping to go from the species labels that are defined in the metadata to the species labels that are used by our species classifier, just to unify them into a common taxonomy. So this
is an example of a step you almost always have to do because
it's also
somehow it's unlikely that the way you've labeled your categories is going to be the same way that the machine learning model has labeled the categories. So I'm sure many of you are familiar with the concept of taxonomic mapping. This is basically like some version of just mapping between whatever you have in your data set to what the machine learning model expects. So you can match them up.
Yeah. Yeah, so for example, the dataset labels the otter the European otter, whereas our classifier calls it the Eurasian otter. So yeah, this is just something you'll have to do, unfortunately. And yeah, then we get a row for each image, basically telling us, the location the image is coming from, the file name. And then we also have the human labeled species common name in the correct taxonomy. Okay, so now we're going to add the classifier predictions to this table as well. Right now it only contains the ground truth labels. And I'm not going to walk through this code in detail, but it's basically just reading in the JSON and mapping it to the table we already have. And this can take around 30 seconds.
How many images are in this data set, Tim?
It's around 11,000.
Oh, no. So
Yeah.
not super big, but
yeah. I think the value, of using machine learning is more like if your data set is in the hundreds of thousands of images. But I think this is a nice, small self-contained example.
I don't know. I mean, labeling 10,000 images also sucks.
True. That's fair. Cool. So now we can also again display our image metadata. And yeah, we now got additional columns for each species that we extracted with the corresponding logit right here. Okay. So now we're gonna first print out again which species we extracted and then focus on a single target species. I'm gonna use the gray wolf, but you can also take any other of those that are listed here. And just
paste
try
it in as the target
paste it in
species, and you can
right
run
here.
this with anything in the list.
Yeah. So if there's anything you are particularly interested in, feel free. And we're also going to set, for now, a threshold for our classifier. I'm just going to set this to 0 for now, but we will tune this later. So run this again.
And
Okay.
remember that the logits have negative and positive values. So setting it to 0 is not the same as saying I want all of them. But we are going to tune it. This is just a starting point.
Yeah. Cool. So now we're going to define a function that goes from our image metadata to an observation table that we can use to fit our occupancy model. And this is a part that I've seen takes up a lot of time in existing occupancy modeling code bases. In this case, it should be almost instant because all the operations use pandas, and pandas is just surprisingly fast for this type of thing. So first we're just gonna take a subset of our image metadata. So we're just gonna take the daytime and the camera location, identify our columns. And then we're gonna define our observations as all the gray wolf scores that are above our defined threshold. And this is basically going to give us a binary observation table. We're then going to define an aggregation window because we have this, continuous set of camera trap images, but we'll need to aggregate that somehow to feed it into our occupancy model. And so we're gonna group by daytime and over this aggregation window, and then sum over all our observations. And then finally, we're going to pivot the table such that we have the different sampling times as our columns and all the different sides as our rows. And then finally, because we summed over all observations, we're gonna convert those into 0 or 1s, depending on whether we have 0 observations or more than 1 observation, or equal to 1 observation. And yeah, this is how this then looks. So we got
Essentially instantaneous, which is nice.
yeah. So we got one row per camera trap and then one column per sampling occasion, which is what we want. Okay, cool. So that's a lot of data pre-processing. Now let's actually fit some occupancy models. We're going to use Biolith, which is our library. You can, and you probably should, absolutely use more mature libraries such as occupancy as well. But yeah, today we're doing everything in Python, and so we're going to use Biolith. It's super easy to install. You basically just do pip install Biolith. Pip is the package manager for Python. And yeah, cool. So we're going to import a standard occupancy model from Biolith and also a utility function to fit this occupancy model. We are only going to use sites that we actually have observations for. We're going to use the degree of area or the degree of burn in the area as a covariate. We're going to normalize the covariates to have 0 mean and a standard deviation of 1. We won't use any observation covariates for now. And yeah, fitting the model is super easy. You basically just to fit, then the model you want to fit, and define your covariates, your observations, and then you say whether you would like to model false positives or not. One interesting thing I found is that in a lot of the occupancy modeling literature, false positives are only modeled for unoccupied sites, whereas really you would expect there to be false positives even for the occupied sites, at least with this setup, right? So our tool supports both. You can either do false positives unoccupied to only model false positives for unoccupied sites, or you can just do false positives constant, model false positives for all sites. Your choice. I'm going to do this for now and just run this.
And how is it fitting the model?
So yeah, great question. It's using Markov chain Monte Carlo. Specifically, it's using the no U-turn sampler or NUTS. We're also going to explore this a bit down the line.
Cool.
And so, yeah, we can print some summary statistics. So basically estimates for our parameters, their standard deviation, median, 5 and 95% intervals, the number of efficient or effective samples. The higher, the better. Usually this should be close to 1,000, ideally. And we also want to look at our head parameter, or indicator, sorry. And ideally this should be close to 1, which it is, which is perfect. And we also got 0 divergences. So yeah, this is looking pretty good. This is kind of the density of occupancy probabilities we're estimating. So most sites in our estimate have around 0.6 occupancy probability and sometimes are much higher. Our estimate for the false positive probability is pretty high, so around 9%. And especially with more rare species like the gray wolf, this seems very high. So I would say this already indicates that we probably picked our threshold to be too low. And so let's actually implement the strategy that we presented for picking a good threshold. We're first going to define this function to basically sample uniformly across logits. Again, I'm not going to walk through this in detail. Let's say we're sampling 20 images for human review. We're then going to call this function and just show the images we are sampling together with their predicted logits and also the ground truth label. In the real setting, we would then have to label those images, but in this case, we already have the ground truth label, so we're just going to show them. So yeah, in this example, our classifier is pretty certain this isn't a gray wolf, as indicated by the relatively small logit. And yeah, the ground truth label is moose. And we can now visualize samples where our classifier is less sure. It's not a gray wolf.
So if you go up, so right at this point, this is the first one where our previous occupancy model fit would have assumed that this was actually a gray wolf because we said any logit greater than 0, we were going to count as a gray wolf.
Yeah.
But in this case, this one is actually not a gray wolf. So this is already like an obvious signal that, potentially we weren't picking the best fit.
Yeah. Yeah, and again, in this kind of area, so around a logit of 0, there are often a lot of unclear images.
And just to be clear, we're not suggesting that these logit values are what you should sort of generally use or assume. The kind of relative values of logits are going to depend on your data.
Yeah.
And so that's why this process of trying to determine what a reasonable threshold is actually quite generally important when you're working with machine learning models, because you can't assume that some sort of metric or optimal threshold set on one set of data is going to be the same for a new set of data. So this is also like, for example, when people use the mega detector to find, empties versus animals, we'll actually have them go through and like based on their use case, based on their sort of needs and based on what they're looking at, try to at least qualitatively pick a reasonable threshold where they think they're not getting too many false positives or false negatives. So this concept of tuning the threshold or the operating point for a machine learning model for your specific problem is one that you should always have in your sort of system. You should always sort of not work with models off the shelf. There's probably a better sort of usable point for a model based on your specific data.
Yeah. Yeah, so this is the first instance where the ground truth label is actually gray wolf. And interestingly, our classifier seems to agree. The logit is pretty high. I would love anybody's input on this. I don't see a gray wolf in here.
Maybe
I
like
might also
we
be
had
blind.
like high quality or was zoomed
Yeah.
in or changed the contrast or something. But yeah, I agree. It
I don't know.
seems dubious.
Yeah, but it's an interesting example, I guess. Yeah, and then basically from here on out, I think all the images actually contain gray wolves. I think this is another instance which is kind of dubious. I haven't seen a gray wolf in here.
I don't know.
Yeah. Okay, so I'm just going to go through these really quick. Cool. So we've labeled our 20 images. And so now we can just sweep over all possible thresholds to find the optimal one according to the F1 score. And so the result is the best threshold in this instance using the samples around 5 with an F1 score of 0.93, which is pretty good. Okay, so now we'll recreate our observation table, but this time using our tuned threshold. And again, we can look at table. And yeah, we now got a lot less observations in here, which is just because we have less false positives, right? Okay, so let's fit the model again. Everything else remains changed. And so yeah, now our model estimates a false positive probability of 0.
In most
Um,
cases.
Yeah, which we can check later. But yeah, again, the number of effective samples is pretty high. Our R-hat diagnostic is perfect, 0 divergences. But yeah, now our estimated occupancy probabilities are much lower than before. Probably much more closer to the true occupancy. Since we have the ground truth labels, we can also check what the actual false positive rate is. And yeah, it's actually super low. So the estimate right here is pretty good. We might also want to inspect the model fitting process more visually. And for this, I found Avis to work perfectly. So let's install Avis. And then plot the trace of our MCMC. So yeah, this is basically just another diagnostic tool to see whether your results look okay. In this case, our estimates for the occupancy and also for the covariates are pretty spread out, so very uncertain, which is just because we don't have a lot of sites, just because the data set is pretty small. And yeah, our estimate for the false positive probability, again, is pretty low, as we can see here. Probably most useful for assessing whether your MCMC has been running successfully is inspecting these traces right here. So ideally, you want these to be super zigzaggy and not like straight lines or anything. And yeah, that's pretty much the case here.
Why do we want them to be zigzaggy, Tim?
That's a great question. I think it's just you want basically you want to sample a lot of different values. Yeah. So yeah, you want to make sure you're basically sampling from a specific range and not just constants. Yeah. So this has been a super simple example of how to use machine learning scores for occupancy modeling and do it everything in Python without having to resort to using R. Yeah, I hope this has kind of demonstrated that you can do this using a super simple strategy. Yeah, let's get back to the presentation. Oh. Well, so how do we go from there? I think the most important takeaway is that, again, you can do this in Python. You don't have to, but now you have the option. These super simple strategies can work, but ideally we would like something more principled. And so for this, we hope to see more innovation at the intersection between machine learning and ecology, and specifically how you take these machine learning scores and incorporate them into ecological models. And we think there's still a lot of opportunities in this direction. And there have been some works For example, this work by Tessa Reinhardt, which is basically one option to incorporate these scores in a more principled manner.
So actually using the continuous scores instead of trying to pick an optimal threshold.
Exactly. Then again, I think it's super hard to actually compare the performance of these different occupancy models on real world data. It's kind of easy to do on simulated data, but on real world data, it's kind of hard. And so I think this is one of the roadblocks kind of stopping the adoption of these new kinds of models. And so, we're currently working on a paper comparing these different model types and also strategies to incorporate machine learning outputs. So this is coming soon, and stay tuned. And finally, BioLith is open for collaboration. So if you have a specific model you're interested in, or if you want to use this, please feel free to just send pull requests or just contact me via my email.
Yeah, and I think we're actively working also with another student to sort of expand the set of models that are included. So if you have suggestions for models that you'd really like to see, we're really open to that. But we also would love if for those of you in this room who are super Python literate, who are interested in maybe seeing some of your more complex occupancy models that you've proposed become more accessible to the community at this intersection, we'd be super, super open to open source collaboration. So people basically pushing their own models into the repo. And the way it's been set up, that should hopefully be reasonably simple. And if you haven't already worked at all with NumPyro, it really is, it's a pretty amazing library, and it has made a lot of this type of probabilistic work a lot more tractable in Python.
Yeah.
And I guess we could go to the next page we wanted to thank our collaborators, in particular, Lauren Harrell at Google, who I've been working with on some of this stuff for quite a while. And before NumPyro came out, we were really bashing our heads against like, how can you actually implement this stuff in Python? Struggling through some like probabilistic JAX formulations and like a bunch of other existing repos in it. So my personal experience is that, as the libraries from the statistical community, from the probability community are getting pulled into Python, and also just as the community of researchers, not necessarily in quantitative ecology, but just in statistics, are thinking a lot more about the intersection of statistics and machine learning, completely separate from ecology. We are starting to see a lot more of this stuff get built into Python and modeled end-to-end in Python. So I do think that regardless of sort of where we all end up, there is going to be a lot of development at that intersection of statistics and machine learning going on sort of across a broad set of applications. And we also wanted to thank Mary Clapp from the Institute of Bird Populations, who's been a very strong ecological collaborator on all of this.
Yeah. And also, we definitely like to thank the Wildlife Insights team and also the team at Google who worked to open source the SpeciesNet classifier.
Specifically, Stefan Est, right?
Yeah.
Was the person who really made that possible. It was a huge amount of work on his side, and it's really exciting to see it out.
Yeah. And finally, I'd like to thank IBM for financial support and also Natural State for being awesome collaborators and providing a lot of the data sets we're working with. Yeah. Awesome.
Very open to questions, discussion, comments.
Yeah, thank you guys so much. I think I'll speak for everyone and say this was really fantastic. Super, super cool to see this end-to-end framework being done. I mean, that's kind of like things you'd think about happening in the future. So seeing it actually happen is pretty sweet. So we do have a few questions, so I'll kind of help moderate those. And for those of you who are there, feel free to put more questions on there, and I'll get to them, and also upvote ones that you want me to ask. So the first one I'll get to is, I wonder if you can talk more about methods for quantifying uncertainties when running these models.
Yeah. So I guess first of all, the nice thing about these Bayesian models is that we can kind of propagate the uncertainty end to end through the model. And so basically, so we haven't done this yet, but it's definitely on our radar to basically try to model the uncertainty at the classifier level and then propagate that through the ecological models, end to end, then to the parameter estimates.
Yeah.
So yeah, I'm not sure this has really been done in a practical way yet, but it's definitely possible.
I think there's some work by Andy Royal's group that's
Mhm.
tried to look at this. I think one of the things that's very challenging in terms of modeling the uncertainty in machine learning models is that those uncertainties tend to not be very simple. So, one thing that people are actually doing when they sort of use machine learning models and then to process data and then try to actually run something like an occupancy model is they assume some amount of human verification in terms of selecting, for example, that threshold that you're going to use. Like this is what the big bioacoustic spotted owl program does. And actually there's a shift towards recognizing that those thresholds are maybe not universal, but actually due to some of the ways that the ecological covariates, such as, a bioacoustic sensor being put right next to a stream, and then the sound of the stream actually impacting the ability for the model to recognize the species, those thresholds might actually need to be sampled per sensor, or there's potential opportunity for thinking about trying to do per sensor thresholds. But also, I mean, even within a given sensor, like there's going to be changes, for example, in weather over time. And so I do think that this type of uncertainty, like being very principled and statistically estimating uncertainty for machine learning models, often ignores the fact that these machine learning models are quite codependent, perhaps, on some of the underlying ecological covariates we might be interested in modeling directly. So I think that's like a bigger sticky can of worms that we're all going to have to grapple with, but I just have seen it completely ignored because we don't have the ability to kind of think about these things end to end. So I'm hoping that actually we'll start to see more people trying to think about what makes a principled approach to handling the dependencies in machine learning models, or sort of the lack of independence from some of the covariates in terms of the model performance.
Yeah.
Fantastic. So next question, what do you think of using Rust for these analyses instead of R/Python?
It's the same problem as the other stuff, right? Like the machine learning is happening in Python. So if you want to learn another language and do the translation, that's fine. But I think if you want to meet the machine learning community where they are, which I do because I'm in the machine learning community, but you guys can do whatever you want, then it's just the same problem as doing it in R.
Yeah.
In terms of that translation, at least.
Yeah.
But Rust is a very cool language. I'm not saying it's not, right? It's just machine learning doesn't happen in Rust.
Yeah. I guess so. I'm not a huge fan of Python overall, but I think it's great for prototyping. And so I think it lends itself very well to, machine learning, which is often super fast moving and super iterative. So yeah, I think machine learning is gonna keep using Python for the foreseeable future, even although Rust is a great language. And I think what is also underappreciated often is how well Python is integrated with a lot of different libraries that facilitate GPU acceleration.
Yes.
And I mean, there's stuff for Rust as well in that area, but I think the Python stuff is just much more general, much more mature. And yeah, I think GPU acceleration is definitely becoming even more important over time, especially as data sets grow larger and larger. And so yeah, I'm not opposed to doing this in Rust, but I think for now Python is best bet.
If only there was time to learn every programming language, right? That's where the bottleneck happens. So let's see, a few more minutes. Let's get to a couple. I'd be curious to hear your thoughts on this one. So unless there's some kind of package-specific restrictions, users should be able to call R code using RPy2 in Python. So I guess I'd be curious to hear, since there are so many R users in ecology, what you all think of that library and its feasibility.
So I love that library, and we've actually worked with that library. You know, we've used it for the paper we're working on right now. I think it's a great option for a lot of people. I also think once you try to do something slightly different, for example, in the Python code, right? If you're trying to modify your machine learning model somehow, I think that quickly becomes intractable to do using these bridges, right? These wrappers. And I think, Sarah, you talked a bit about this.
Yeah, like you just if you're trying to get under the hood at all, in either the machine learning or into the statistical modeling, if you want to actually tweak something from the kind of basic settings, that's where all of this wrapperization starts to really bite you in the butt. And this is true also of the kind of wrappers around machine learning code in R. So for example, that quick tweak that Tim made at the beginning to be like, we don't want just the 5 top confident predictions like with a softmax score, we want the logits. Super easy in Python. If you had that wrapped up in R, I don't know that it would be possible.
Yeah.
Without like a huge amount of work. And honestly going into the underlying Python code in the first place. And so that's then what's the point?
Yeah.
But
And,
yeah, I think I have very mixed feelings about wrapperization. I mean, even inside Python, there's a lot of wrapperization that's sort of happening, like going from PyTorch to PyTorch Lightning. It's like, okay, well, we've wrapped a bunch of the stuff and now you can do everything in less lines of code. But as soon as you want to get under the hood at all, it ends up being much more trouble than it's worth. And we often end up kind of going back to kind of like the more simple solutions. But I think that has a lot to do also with the capabilities. But even I run this CV for Ecology program, which if any of you are interested in learning more about the machine learning under the hood, be more than welcome to apply. We just ran our third version of it. But we bring in a bunch of ecologists, quantitative ecologists, statisticians, but ecologists who have a bunch of data that they want to build a machine learning model to help process. And we have them write all of their own code in Python and PyTorch to, train and evaluate and maybe even deploy those machine learning models. I can send the link out after, but it's just CV4 number 4 ecology. And with that, what we found is that you can do a lot with those kind of wrapperized versions, even in Python, but almost inevitably, every real world application needs some adjustment. There's going to be something specific to your data, specific to your model, specific to the needs that you have in terms of the output, where it's too variable. The use cases are too variable. And so then you end up almost always needing to get a little bit under the hood, just a little. And as soon as you have that wrapperized package, it just gets so much harder. So I'm kind of frustrated with them in terms of like just someone who actually has a real use case where they're going to need to tweak some stuff.
Yeah, and just to add to that, I think this is especially true if you're trying to really debug code. So like step through code line by line, right? This works for one language, but not for like mixes of 2 languages where one is wrapped in the other. So yeah.
Yeah.
Awesome. It's kind of a constant battle with usability and maintenance and digging into the foundations. A couple other ones. How well does SpeciesNet cope with classifying very similar species? So something like different deer species or classifying species that show extensive variation, for example, domestic dogs.
I will point you to the to crop or not to crop paper that we published about the SpeciesNet model, as well as kind of the blog post and the model itself. There's a bunch of sort of relative discussion of this. In general, hard things are harder than easy things. Like it's really easy to categorize like an elephant versus a giraffe, and it's much harder to categorize fine-grained species of deer. Now, these machine learning models are getting, when they have a huge amount of training data, they're actually very capable at picking up those fine-grained differences. But then it really just comes down to did they have sort of sufficient training data? And sufficient here doesn't mean sheer number. It means capturing the variation and how you're actually going to see that species. So in different environments, different contexts, different poses, so that it's sort of not learning particular biases. And if it has that, we have found that they can be very robust to quite fine-grained challenges. Now, the flip side of this, and I think Roland Kayes has a paper about this, there are a bunch of species that arguably maybe shouldn't be identified in images. Like actually human experts are not able to, with statistical significance, agree on the species. And so I think sometimes there's kind of this alternate question, which is this thing actually identifiable in this image at all? Versus like, can a machine learning model learn to predict what a human will say? So yeah.
Awesome. Next one, just ran my first species net test yesterday with a winky face. Thanks for your great work. How does the geographic filter work for so many species?
Oh, we're just going to species net Q&A. If anyone has any questions about the statistical stuff, let me know. So the geographic filter is currently essentially a human expert curated like yes or not list. So essentially it's just saying for a given place what species are known to have sort of ever been seen there. It's a pretty hard filter at this point. Fascinatingly, even though like with iNaturalist, they have increasingly good geographic, like geoprior models or sort of geospatial models, it turns out that those models are capturing iNaturalist distributions in ways that are maybe not exactly the same as camera trap distributions. So I think there's definitely a lot of potential in moving to a more sort of end-to-end model of the functional space of the world and kind of like the continuous score probabilities of something like the distribution of species. But for now, it seems like just these more expert-driven, knowledge-driven hard filters are a really nice benefit.
Awesome. So I got a couple more here. It is 1:30 though, so let me know if you guys have to run off. We have curious to hear your thoughts on using INLA instead of traditional MCMC here. Sometimes MCMC can take some time.
Sorry, what was the first?
They're curious to hear your thoughts on using INLA as opposed to traditional MCMC.
I'm sorry, I'm not sure I understood or know that term.
I think it's just another fitting.
Okay. Yeah,
If
I'm
it's
not sure.
supported in NumPy, you can swap it out.
Yeah.
Like, I mean, bring your own favorite mechanism. We used MCMC for this tutorial because it's pretty straightforward. I think there are a lot of pros and cons with a lot of different types of, mechanisms for fitting models. And so depending on your data, your use case, it might really speed things up, and that might be really beneficial.
Yeah. Again,
Yeah.
if you the MCMC fitting is pretty quick,
Fast.
but yeah, that's only if you have a GPU.
Yeah. I know this is kind of a bigger discussion or can of worms, but I do think that we're starting to see more and more of these some of these discrepancies in terms of people's ability to participate or have access to kind of what is like the forefront of machine learning or even in these days things like statistical modeling based on how accessible like these kind of expensive high-powered computing systems can be. This has always been true, right? People who are at institutions with huge, centralized computational infrastructure are able to run much fit much larger models, potentially train much larger machine learning models. Data is another dimension of this. If you have access to the data to train, you can train a better model. And I think that we're definitely not seeing those inequities going away, but I am very, very excited for that reason about people focusing on the development of efficient machine learning models, either mechanisms to train them efficiently to start with or to run inference efficiently, which really just decreases that computational cost of processing the data in the first place. And similarly, I think there's been some nice work on GPU enabled or not GPU enabled efficiency and sampling, which is probably like what you suggested.
Yeah, that's great. That's great. So we have two more questions here and a couple of comments. So first question, have you seen spatial dependence being introduced into the probability of detection?
Yeah, so that's definitely something we want to do, but haven't implemented yet. So yeah, all the models currently implemented are not using any kind of spatial information, any kind of spatial autocorrelation.
If you're someone who, I mean, we are working on it too, but if you're interested in that, or if you're someone who's been developing that type of model, we would love to work with you to implement those in this code base.
Yeah.
Fantastic. Okay, and one more data question. Is the data used to train SpeciesNet open source? And if so, where is it?
No, the data is all the wildlife insights data. So some of it is open to the public and some of it is not. And I think that there's a lot of dimensions of complexity with open sourcing data that you may or may not also have with open sourcing models. So this was kind of the mechanism of workaround that Wildlife Insights could build with all of their partners in terms of trying to build something that was accessible to the broader community, but without potentially releasing data that is either still under embargo or contains potentially like information that that institution doesn't feel comfortable releasing to the public, whether that's capturing images of humans that may or may not have consented to that, or capturing images of endangered species that they're worried about people finding the locations of. So I think it's I think that we are very, very far from seeing Wildlife Insights scale data being completely publicly accessible. That said, if you are interested in training fully open source camera trap species models, the Lila.science platform is an amazing starting point. Dan Morris, who's also at Google, has been leading that since back in his Microsoft days. I was an early contributor, and it's essentially all of it is in a centralized taxonomy. There's mappings between the different categories, and so it's kind of possible to train on all of that data publicly.
Great.
I think the day that we fix or figure out how to handle the complexities of data sharing and ecology is probably I'm realizing that it's further away than I had initially hoped when I got into this space. So I think there's a lot of complexity around sharing data.
Yeah, those are great points. So I think that's let's see about it. Oh, there's a few more coming up here. Okay, so yeah, so a few comments I'll just share. Comment saying this is amazing. Comment that kind of echoed what you were saying about wrappers, Sarah, kind of being unstable in the long term. A comment on moving the ecology code community to Python will also allow for integration with QGIS and the broader FOSS4G ecosystem. And then yeah, a comment from Jay Redwine at fiu.edu saying there's interest in spatial dependency for vegetation patterns for a topic there. So yeah, so I think that is about it. So again, thank you both so much. This is really fantastic. Looking forward to seeing all of your work come out.